We have been reviewing topics in probability and random process. This would be the last lecture as a part of this review. We will quickly recall what we did in the previous lecture. We discussed properties of Gaussian random process, Poisson process, simple random walk, Wiener process, Brownian motion, random pulse process and Gaussian white noise process. So, we will have opportunity to return to some of these processes later when we use them to model loads and responses. We also introduced the notion of mean square derivative that was based on mean square convergence of random variables in the sense of mean square. I briefly touched upon the topic of two random processes in the previous lecture. We will continue with that. So, let us consider two random processes u of t and v of t. The description of u of t, to recapitulate, is in terms of first order probability distribution function or second order probability distribution function, or in general the nth order probability distribution function. Associated with this, we also have the nth order probability density function. We could of course define expectations, this is a mean, this is covariance and so on and so forth. So, this completes the description of a random process u of t, and we say that u of t is completely specified if I am able to specify the nth order joint density function for any choice of this t1, t2, t3, tn and for any choice of n. In a similar vein, we can completely describe random process v of t, nth order density function or expectation, so on and so forth. Now, when it comes to a question of joint description of u of t and v of t, we can consider two time instants t equal to t1 and t equal to t2, and I select one random variable u of t1 from ensemble of u of t and another random variable v of t2 from ensemble of v of t. So, this can be viewed as the joint probability distribution function of the random process u of t and v of t at two time instants. So, this can be generalized for n time instants from ensemble of u of t and some other m time instants from ensemble of v of t, and if I am able to specify this kind of joint probability distribution function or the associated probability density function, we can say that the two random processes u of t and v of t are completely specified. We can also define the moments with respect to these joint density functions. For instance, I can define what is known as cross covariance function, which is actually the expectation of C of u v of t1 comma t2 is expectation of, suppose mean is 0, suppose if I assume u of t is 0 and v of t is 0, this is nothing but u of t1 into v of t2. If mean is not 0, this is what I have shown here, this is expectation of u of t1 minus mu of t1 v of t2 mv of t2 into this density function, and this double integral gives the cross covariance function between u and v. The word cross originates from the fact that the random variable u of t1 emanates from ensemble of u of t and the random variable v of t2 emanates from ensemble of v of t. So, this is in contrast to the definition of autocovariance function which we introduced previously, where I talked about two random variables originating from the same ensemble. So, the word, although both functions are covariances, we add this prefix auto and cross to indicate the choice of the underlying random variables. The notion of stationarity can be generalized to stationarity of two processes. Suppose we ask the question, when do we say that u of t and v of t are said to be jointly stationary? First of all, u of t must be stationary, v of t must be stationary in the chosen sense of stationarity. Suppose we are talking about wide sense stationarity. u of t should be wide sense stationary in its own right, v of t should be stationary in its own right. That would mean mean of u would be a constant, mean of v would be a constant, and autocovariance of u of t, that is CUU of t comma t plus tau, will be a function of only the time difference. Therefore, CUU of t comma t plus tau would be CUU of tau. Similarly, CVV of t comma t plus tau is CVV of tau. The additional requirement for wide sense stationarity of two random processes is that the cross covariance function should also satisfy this requirement. That is CUV of t comma t plus tau must be function of the time difference tau. In the same sense, we can also discuss about strong sense stationarity in terms of probability density functions. So, I take joint density function between a random variable originating from u of t and v of t at some time difference, and based on the notion of stationarity that we considered for u of t, we could extend the definitions and we can talk about strong sense stationarity of two random processes. Now, let us look at what exactly is meant by we talked about CUV of is expectation of u of t 1 v of t 2. So, I will call it as CUV of t 1 comma t 2. Suppose you have an ensemble suppose this is ensemble of u of t and this is an ensemble of v of t. What we are saying is there is a time instant t, there is another time instant t plus tau, there is this same time instant t and time instant t plus tau. So, there are basically 4 random variables here, 2 from u of t and 2 from v of t. When I say CUV of t 1 comma t 2, it is from u of t 1, that is this is t 1, say this is t 1 is equal to t and this is say t 2, say t 1 equal to t, this is equal to t 2. U of t 1, that is this, and v of t 2, that is this. This is clearly different from the covariance between these two random variables. Okay. So, this is also equal to, that is this is also equal to expectation of v of t 2 into u of t 1. So, this is v of t plus tau and u of t. So, this can be written as CVU of t 2 comma t 1. The point that I am making is this is not a symmetric function, okay, because if you simply consider CVU of t 1 comma t 2, then you will be looking at correlation between two other random variables. For example, if you now consider CVU of t 1 comma t 2, this is correlation between this random variable and this random variable. So, there is no reason why the covariance between these two random variables should be same as covariance between these random variables. So, it is not symmetric because there are 4 random variables we are talking about. So, we can write this information on covariance in the matrix form C of t 1 comma t 2. CUU of t 1 comma t 2 is the autocovariance of u of t. CUV of t 1 comma t 2 is cross covariance between u of t 1 and v of t 2. CVU of t 1 t 2 is cross covariance between v of t 1 and u of t 2, and this is CVV of t 1 comma t 2 is autocovariance of v of t 1 and v of t 2. This is not symmetric because we are not talking about covariance between the same two random variables. There are 4 random variables. So, although this is a covariance matrix, it should be understood that it is not in the sense of covariance between 2 random variables. There are actually 4 random variables here. That is why this asymmetry arises. C of tau is this. If this process is stationary, this will be, suppose T is T1 is T and T2 is T plus tau, this is the covariance matrix. So, this is what I am trying to say here, C u v of tau is u of t into v of t plus tau. So, this is commutative, I can write this first and this next. This is v of t plus tau u of t, and this is nothing but C v u of t minus tau. Therefore, C u v of tau is C v u of minus tau. So, in some sense there is a kind of an anti-symmetry we can see here. Okay. So, this should be understood. What is the corresponding definition of power spectral density functions? So, we define power spectral density matrix of power spectral density functions. SUU of omega is the auto power spectral density function of process u of t. U of t is taken to be stationary and we will also assume that it has 0 mean. SUV of omega is known as cross power spectral density function between u and v. This is SVU of u, this is SVV of omega. So, you recall how did we define SUU of omega? It was limit of 1 by t expectation of xt of omega into its conjugate. Now, if you replace omega by minus omega, what happens? This will be xt of minus omega, this is xt star of minus omega. Xt of minus omega is nothing but xt star of omega, and xt star of minus omega is nothing but xt of omega. Therefore, SUU of omega is SUU of minus omega. Now, if you now consider SUV of omega, this is expectation of ut of omega, vt star of omega. I think here there is a mistake here, this SUU of omega, this x should be u. SUV of omega is defined like this. Now, if I replace omega by minus omega, so this is ut of omega is ut of minus omega, vt star of omega is vt star of minus omega, this is ut star of omega and this is vt of omega, therefore, this is SVU of omega. Now, you take conjugate of SUV of omega, this will be defined as ut star of omega, vt of omega, because you are taking conjugation on this. This is nothing but SUV of minus omega. The point that you have to notice is SUV of omega, which is a cross power spectral density function, is a complex valued function. It has a non-zero real part and a non-zero imaginary part. You can show that this indeed is the Fourier transform of the cross covariance function. We were assuming mean to be 0, therefore, there is no distinction between cross covariance and cross correlation function. So, this is cross correlation because mean is 0. This is a Fourier transform pair constituted by SUV of omega and RUV of tau. Since this is not a symmetric function, SUV of omega will have a non-zero real part and an imaginary part, and we can write it in the polar form as an amplitude and a phase. So, this amplitude we call it as amplitude of cross PSD function, and this is a phase spectrum. The real part of SUV of omega is called co-spectrum and the imaginary part is known as quadrature spectrum. This is a nomenclature. Later on when we model earthquake loads using multiple random processes, we will have occasion to use some of this nomenclature. We can introduce what is known as complex coherency function, which is SUV of omega divided by square root of SUU of omega SVV of omega. This again is a complex function and the modulus of this complex function is known as coherency. This coherency you can show that it takes values between 0 and 1, and if u and v are independent, you can show that coherency will be 0, and if they share u and v share a linear relationship between them, the coherency will be 1. So, this again is somewhat analogous to the cross correlation function that we were discussing earlier. We will consider a simple example where I define two random processes u of t and v of t in terms of a parent process s of t. I call u of t as s of t and v of t is s of t plus alpha. Let s of t be a stationary Gaussian random process with 0 mean. So, what is the coherency or a cross power spectral density function between u and v? That is a question. C uv of tau can be expressed as expectation of u of t into v of t plus tau. Of course, mean of u and mean of v are 0 because mean of s and s is stationary and mean is 0. Therefore, expected value of u and v would be 0. So, u of t is s of t, v of t plus tau is s of t plus alpha plus tau. Therefore, this is CSS of alpha plus tau. This is t plus alpha plus tau minus t, this is this. So, if you consider now the Fourier transform of this, we get the cross power spectral density function between u and v. This is given by this C u v of tau exponential minus I omega tau d tau. So, using this relation for C u v here we get this. We can now make a substitution beta as alpha plus tau and limits of integration would remain unchanged, but there will be C alpha plus tau will become CSS of beta and this tau will be beta minus alpha, and if you use that we get S u v of omega is exponential of I omega alpha into SS of omega. This would mean coherence u v of omega is exponential I omega alpha. We can consider a similar problem. Again there is a parent process S of t and yet another process W of t. U of t is S of t and V of t is S of t plus W of t. S of t is taken to be a stationary Gaussian random process with 0 mean and W of t is 0 mean Gaussian white noise process which is independent of S of t. The question is what is coherency between u and v? So, this is an exercise that you can try. We now briefly touch upon question of how to deal with non-stationarity. One of the simple technique to deal with non-stationarity is to express a non-stationary process x of t as a product of a stationary process s of t and a deterministic envelope function or modulating function. E of t is a deterministic envelope function. S of t for purpose of illustration will take it as 0 mean stationary Gaussian random process. X of t would be Gaussian because this is a linear transformation, it is a constant into a Gaussian quantity. So, the x of t would also be Gaussian. In modeling earthquake ground acceleration, this is one of the popular models that we will be using. We can see first how it looks like. The black line that you are seeing here is x of t and this red line is actually the envelope E of t. So, this envelope multiplies a sample of a stationary random process and what we get is this black line. So, I am talking about modeling of x of t where non-stationarity has this kind of transient behavior. This is typically how an earthquake record might look like. It will last for about 30 seconds and there is a strong motion phase and a gentle decay. So, we are interested in characterizing the behavior of the structure during the strong motion phase, and that is what typically we are interested in. So, a brief description of this random process can be obtained by considering its mean and covariance function. Since x of t is Gaussian, the mean and covariance function completely specify x of t. So, what is expected value of x of t? Expected value of x of t is expected value of E of t into S of t, which is 0 because expected value of S of t is 0. Then expected value of x of t into x of t plus tau is nothing but E of t into S of t, E of t plus tau into S of t plus tau, then this is E of t into E of t plus tau and RSS of tau. So, the covariance of x of t now depends on t plus tau. This is of course a stationary part, but x of t by virtue of presence of these two terms continue to be non-stationary. If you consider for example tau equal to 0, this expectation is nothing but the variance of x of t, and you can see here that variance is e square of t into sigma s square. That would mean the variance or the standard deviation is a function of time. So, it is not a wide sense stationary process, and since its process is Gaussian, even the first order density function will be changing with time, therefore, it is not stationary. There is one property which will be very useful in modeling, that is known as Markov property. We use the term Markov random processes. It should be noted that Markov property does not describe a distribution function. For instance, a Gaussian random process refers to the fact that at a given time t, the random variable x of t is Gaussian distributed. So, you take two random variables, they are jointly Gaussian and so on and so forth. When I talk about Markov processes, there is no underlying probability distribution that I am talking about. For example, a Gaussian random process could have a Markovian property. So, what is this Markovian property? Let us consider a random process x of t. Let us assume that it has continuous state and the time parameter t is also continuous. We will consider n time instants t1, t2 up to tn ordered in this particular manner. This defines n random variables x of t1, x of t2 and so on and so forth, x of tn. To characterize a Markovian property, we need the conditional probability distribution of x of t1 less than or equal to xn. So, I consider the probability that x of t1 is less than or equal to xn conditioned on the fact that x of tn minus 1 is less than xn minus 1, x of tn minus 2 is less than or equal to tn minus 2 and so on and so forth. If this is equal to x of tn less than or equal to xn conditioned only on the value of x of tn minus 1 at the previous time instant, we say that the process is Markovian. This should be true for any choice of n and any choice of t1 and tn. That means, if you imagine that nth time instant defines the future and n minus 1 time is the present, what Markovian property says is that future depends upon the present and not on the past. How the present was arrived at has no bearing on what happens tomorrow. Okay, it has so called one step memory. You recall when I talked about white noise or a sequence of independent random variables, they have no memory, there is no memory there. Here there is one step memory. So, in terms of distribution function, the Markovian property is described as the probability distribution function of at tn, that is xn comma tn, conditioned on xn minus 1 tn minus 1, xn minus 2 tn minus 2, so on and so forth, is equal to probability distribution of xn comma tn conditioned on xn minus 1 tn minus 1. The fact that you know all this has no bearing on this function. Associated with this, we can define the nth order probability density function. This also displays the same trait, that the knowledge of what was happening from t1 to tn minus 2 has no bearing on this function. So, again you can see there is a one step memory. So, how do we describe a Markov random process? We can start by talking about first order probability distribution function. There is one random variable x of t1 that is completely described in terms of its density function. Two random variables, I will write it in terms of joint density function or a conditional density function and a first order density function. How about third order probability density function? This can be defined in terms of a third order joint density function or two conditional density functions and one first order density function. If x of t is Markovian, this density function, conditional density function, will be equal to this, because what happens at t3 depends only on what is happening at t2 and not on what has happened at t1. So, this density function becomes independent of x1 and t1. So, here we need two conditional probability density functions and one probability density first order density function. There is a, you can see here, this describes the transition from T2 to T3, this describes transition from T1 to T2, and this conditional probability density function is known as transitional probability density function of the Markov process x of t. So, if you consider now a nth order joint density function, by using this argument we can show that this depends on the first order density function p of x1 t1 and products of n minus 1 conditional density functions, and these are known as I said, conditional probability density functions. So, this is this transition probability density function is called as TPDF, and this is given as p of x nu comma t nu conditional on x nu minus 1 t nu minus 1. So, a complete description of a Markov process is through a first order density function and this transition probability density function. There is a further requirement on this transition density function, which is known as a compatibility requirement or consistency requirement, that can be explained as follows. You consider two time instants t equal to t1 and t equal to t2 and an intermediate time instant t equal to tau. Now, let us consider the joint density function between x of t1 and x of t2, and that is given by x2 comma t2 x1 comma t1. This can be written as probability density function of x2 comma t2 conditioned on x1 t1 into probability of x1 t1. This conditional density function itself, this joint density function itself can also be interpreted as a marginal density function of a third order probability density function. That means, I consider now 3 random variables, one here and one here, and integrate with respect to states of this random variable. So, the second order density function is a marginal density function of a third order density function. Now, let us use the conditional densities now. This I will, since t1, tau and t2 are ordered in the manner that we are talking, probability of x2 comma t2 conditioned on x of tau and x1 of t1 into probability of x of tau conditioned on x1 t1 into probability of x1 t1 dx. Now, the process is Markovian, therefore, this density function can be approximated, this density function, this is same as this, approximated by x2 comma t2 x of tau. Now, please see what is this equality. This equality is between this term and this term. There is p of x1 comma t1 on the left hand side and p of x1 comma t1 on the right hand side, they can be cancelled. So, I am left with p of x2 comma t2 conditioned on x1 t1 is this integral. Now, I have invoked the Gaussian property, and this is the expression I get on the right hand side. What this says is basically, in moving from t2 to t1, the conditional density function should satisfy this internal requirement. So, this is a requirement for the transitional probability density function of a Markov random process. So, this is a consistency condition for the process to be Markov. So, this is the so called Chapman-Kolmogorov-Smilchowski relation. We will return to this later in the course, where we will use Markov property of responses to characterize the probability distribution of structural response to random loads. That will come slightly later in the course. Now, with this we have completed the review of topics in probability and random processes, and we are now ready to start discussing about stochastic structural dynamics or random vibration problems. As a prelude to that, we will begin by quickly reviewing the basic principles of dynamics of single degree freedom systems. As we know, this is the familiar equation of motion for a single degree freedom system. M is the mass, C is the damping, K is the stiffness, and F of t is the excitation. x naught and x naught dot are the initial conditions. This dot represents derivative with respect to time. So, this is a linear second order differential equation, it is an ordinary differential equation. T is the independent variable, x is the dependent variable. This is an initial value problem and we need to solve this problem to analyze the response of a structure which can be modeled as a single degree freedom system. I will touch upon certain descriptors of the single degree freedom system in terms of its initial response, impulse response, frequency response function and the concept of resonance, which will serve as starting point to understand for example, the notion of a steady state when f of t is modeled as a random process. If f of t is a random process, what it means is there is an ensemble of f of t. Apart from the fact that at any time t it is a random variable and it is a family of random variables etc., the implication of this on this equation of equilibrium is that this is not a single differential equation. Because f of t is itself an ensemble of time histories, this equation of motion represents an ensemble of equations of motion. Of course, we can take sample by sample and solve this problem, but that is not what we are going to do. The question we would ask is, if I know the complete description of f of t as a random process, that would mean the definition of nth order probability density function for some any n. The question is, what is the corresponding description of x of t? Can I get the complete description of the random process x of t? That would be the first question. Or in other words, how does the uncertainty in specifying f of t propagates through the system and manifest as uncertainty in x of t? If f of t is a random process, x of t is also a random process. So, the basic problem in random vibration analysis of a single degree freedom system lies in answering this question: what is the, given the complete description of f of t, what is the complete description of x of t? This question we will take up shortly, but before we do that, we will restrict our attention to f of t being deterministic. We will begin by considering f of t to be harmonic, say p cos lambda t. A point to be noted in our discussion is the value of this damping C. As you know, there are three possible ranges of this damping value, the so called under damped systems and critically damped system and over damped system. We focus our attention in this course on under damped system, unless I state it otherwise. The default model for damping is that it is systems are under damped. By that what it means is, in free vibration the structure oscillates and the vibrations decay exponentially as shown here. That means there is a oscillatory decay to the state of rest in free vibration, that is when f of t is 0. So, this is an underlying assumption of all our analysis as a part of this course. Of course, I am again restricting attention to only linear systems. If the system is non-linear or it has a different damping model, I will have to explicitly make that exception when I describe the problem. So, in standard notations we divide by m and use the standard notation, whereas eta is the ratio of damping to the critical damping. X double dot plus 2 eta omega x dot plus omega square x is p by m cos lambda t. These are the initial conditions. So, x of t has a complementary function and a particular integral, this. So, the complementary function for this case can be shown to be sums of exponentially decaying harmonics, that is exponential minus eta omega t a cos omega dt plus b sin omega dt, and the particular integral in this case we assume it to be harmonic, a superposition of cosine and sine functions. These constants C and D have to be obtained by performing a harmonic balance of the equation of motion with a right hand side as p cos lambda t, whereas these constants A and B are the arbitrary constants of integration which have to be evaluated based on the initial conditions of the system. So, if we do this harmonic balancing, I get for C this quantity, for D this quantity. If I now substitute those values of C and D, I get the displacement to be given in this form, where A and B are still the constants which are to be yet determined based on initial conditions, and if you actually do that, you can show that A and B depend on x naught and x naught dot through this pair of equations. So, I have determined A and B in terms of system parameters and given initial conditions, and this is a particular integral. So, this is a complete solution. If you now look at the nature of this solution, we can immediately see that x of t is aperiodic, because there is an exponential eta omega t which decays in time. But this component itself, the second component itself, is periodic with period 2 pi by lambda, which is actually the period of excitation. Now, as time becomes large, this exponential eta omega t decays to 0, in which case this part, the first part, goes to 0, and consequently what happens? The effect of initial conditions x naught and x naught dot are encapsulated in these constants A and B. This part is independent of A and B, this part is independent of A and B. So, as t tends to infinity, this entire part goes to 0, and the effect of initial conditions also consequently will vanish from the response. So, if that happens, we say that x of t has reached a harmonic steady state. In that situation, the response is periodic at the driving frequency and is independent of initial conditions. The question that we will be asking shortly is there a counterpart of harmonic steady state when f of t is a random process? That is a question that we have to answer. Before that, we will run through some of the details. So, as few remarks, response is aperiodic for small t. As t becomes large, response becomes periodic. In fact, it is harmonic at the driving frequency. So, there is a transient phase and a steady phase. The transient phase is characterized by a periodic response in which influence of initial conditions are still present. The steady phase is when the response becomes periodic and effect of initial conditions vanish. Does such things happen if f of t is stationary, is a question that we have to bear in mind. So, steady state, for large t, response becomes harmonic and influence of initial conditions vanish. The system indeed takes some time to reach steady state, and that is governed by the factor eta of omega. How does this originate? There is a term eta omega t. So, steady state is reached when this term becomes 0. So, the rate at which this goes to 0 depends on value of eta omega. Larger the value of eta of omega, sooner will be the steady state. If eta is 0, system will never reach steady state. That is, for eta equal to 0, the effect of initial condition never dies and response consists of two harmonics, and sums of two harmonics could be periodic, but in general they are not periodic. So, this is the graphical display of this solution. This red line, thin red line that we are seeing is the total response. That means that transient phase plus the steady phase. So, this is actually the x of t. But on this, if I now plot only the terms which are functions of initial conditions, you can see that they oscillate and go to 0. So, initially if you follow now these full lines, you will see that response is aperiodic, and after some time the amplitudes have become constant, and if you see the phases, they are also constant. That takes some effort, and we say that the system has reached steady state. The notion of harmonic steady state we will see later is related to notion of stationarity. Okay. So, what does steady state mean? Steady state does not mean that x of t becomes constant. Some property of x of t, namely its amplitude and it phase with a forcing function, that becomes constant, but the function itself continues to be function of time, it varies with time. If damping is absent, as I was telling, the initial condition, there is no reason why initial condition should decay, and the blue line is the total response and the red line is the component due to initial conditions, and the total response has 2 harmonics, and this goes on oscillating forever, and initial condition effect is felt throughout the time, all the values of time. Now, we can see a few details about nature of this steady state. Suppose in the expression for x of t we allow t to infinity, the terms that are actually multiplied by e raised to eta omega t go to 0, and what remains is this function. We can slightly reorganize these terms, the details can be digested, but if you actually do that, we can define a non-dimensional quantity which is x, which is amplitude of response of x of t, divided by p by k. P by k is the static response. If I were to apply a static force p, the displacement of the system would be p by k. This ratio is known as dynamic magnification factor, and it is given by this quantity. This r is the ratio of the driving frequency and the natural frequency of the system. This theta, which is the phase, is given by tan inverse of 2 eta r divided by 1 minus r square. So, this dynamic magnification factor tells what is the magnification on the static response, because the system is vibrating under dynamic loads. If I were to plot now this dynamic magnification factor as a function of r and eta, we will see this familiar curve. Here eta is changing along these curves, the cyan line, blue, green and red lines, and eta is changing there, and on x axis the frequency ratio is varying. So, if you, as you see, as r goes to 0, that means driving like cos lambda till lambda is 0, the amplitude will be 1 and there is no dynamic magnification factor, I get as 1. That means this is a static behavior, this is a static point of static behavior. As frequency increases, we see that in the neighborhood of lambda being equal to omega, the dynamic magnification factor climbs up, it is as high as 20, 30, 50 depending upon value of damping. Subsequently, as further increase in r, the dynamic magnification factor goes on reducing, and beyond a point in fact it becomes less than the static response, and we can divide this graph into 3 regions. One is the region here, which is characterized by low value of r, where the stiffness of the system dominates. That means response is nearly static and it is dominated by the stiffness characteristics. Here in the region r close to 1, this is eta dominated. As r becomes large, this behavior is dominated by inertial effects. That means the load keeps changing its sign so rapidly that system fails to recognize that. That means the inertial effects dominate the structural behavior. So, this is mass controlled region, this is damping controlled region, and this is stiffness controlled region. Similarly, if we look at the phase plot, in the region of r equal to 1, the phase rapidly changes and goes through a transition through a value of pi, and a rapid change in phase is what characterizes the so called resonant condition. In the neighborhood of r equal to 1, where there is significant dynamic magnification, we say that structure is under resonance. The precise value of r at which this reaches the highest value is not r equal to 1, it is slightly different, and that is actually the point of resonance. In the phase diagram, the manifestation of resonance is through a rapid change in phase angle. If we now look at this dynamic magnification factor, you see that as damping is reducing, the amplification factor is climbing up. So, the question would arise, if damping indeed goes to 0, what will be the magnification? It appears from this graph that the dynamic magnification factor becomes unbounded. So, what really happens? If you apply a harmonic load on a undamped system near resonance, what really happens? If you want to analyze that, we can consider the equilibrium equation with no damping. Here, this is a complementary function and this is a particular integral, and so let us assume the system starts from rest, and we can show that if we impose these initial conditions, we can evaluate A and B, and if we were to do that, I get this expression. And in this, if I now simulate the resonant condition, namely omega going to lambda or limit of lambda going to omega, what happens is cos lambda t minus cos lambda t goes to 0, omega square minus lambda square, that also goes to 0, it is an indeterminate form. So, we have to use this L'Hopital's rule and get the limit as lambda goes to omega. So, you have to actually differentiate with respect to lambda. So, if we do that, I get this function p t into sin omega t divided by 2 m omega. So, as time becomes large, this is not a periodic function now, although the system is driven harmonically and its system is linear, but at resonance it is not a harmonic, it is not even a periodic function, because as t becomes large, this amplitude becomes large, and in the limit of t tending to infinity, the response becomes unbounded. So, if you plot the time history, you see that there is a linear growth of amplitude as time passes, and if there is a critical limit on the say the force in the spring, which is k into x, there may be at this point the structure would simply break, but it would still survive this 12 second of shaking before it actually breaks. That means, an undamped system resonance does not cause instantaneous failure, the amplitude starts growing, and at some time when the amplitude crosses a threshold, it fails. The description of dynamicals in the description of dynamical system, we introduce what is known as indicial response and impulse response. Indicial response is the response of the system to a unit step function. A step function, if you recall, we defined as u of t minus a 0 for t less than a, and it is 1 for t greater than a, that is as shown here. This is an a is 3 seconds. So, till we reach the value of 3, it is 0, and at 3 it jumps. So, if you actually want value of this function at 3 seconds, you can take the left hand average of the left hand limit and right hand limit, which is 0 and 1, you can call it as half. It is a matter of convention. Now, if we consider the response of the system to a suddenly applied load, we can model the load as a Heaviside step function. So, u of t means there is a suddenly applied load at t equal to 0. Suppose the system is at rest and you apply a suddenly applied load, constant load, we can analyze this problem. There is again the solution will have a complementary function and a particular integral, and if you now select the initial conditions, impose the initial condition x of 0 is 0, x dot of 0 is 0, we can evaluate a and b, and I get this response, and we call this, we denote this by g of t, and this is known as initial response of the system. This is one of the important descriptors of a linear time invariant system. How does initial response look for an undamped system? You can see here, if damping is 0, the this will be 1 and this part is 0, I get 1 minus cos omega t. So, that is depicted here, the function is oscillating about value of 1, not about 0, about 1, because it is 1 minus cos omega t, and this is the undamped initial response. A damped initial response will oscillate about 1, this is 1, So, it will respond and it will decay to a constant value as t becomes large. This is nothing but actually the static response of the system under unit load. As t becomes large, the response of the system is nothing but the static response, because it is a damped system. Now, we can consider the response of the system to a box kind of load as shown here. So, this can be modeled in terms of two Heaviside step functions. This is f in, suppose f is 1, here f I have taken as 1 in this equation. This is u of t minus u of t minus a. So, this is a box of width a. So, I can analyze this response. The response will be g of t for t less than or equal to a, and for t greater than or equal to a, it will be superposition of response due to u of t and u of t minus a, which is g of t minus g of t minus a. Okay, it is matter of I am superposing the force in terms of two functions, and I am superposing the response in terms of corresponding responses to these two forces. So, for a specific case you can see here, this is the response, this is the time at which the box ends, box excitation ends. So, as long as there is a load, it will be oscillating, and the load is suddenly removed, it will oscillate and come to rest. Okay. This is a response of the system to a box input. Now, what we will do is we will shrink this box now. Suppose there is a step function with amplitude f and time tc. Now, I will allow this tc to go to 0, and at the same time I will increase f so that f tc goes to unity. So, this we have discussed earlier when I discussed about discrete random variables and their relation to continuous random variables. We get what is known as, in the limit that I am mentioning, we get what is known as Dirac's delta function. So, Dirac delta function is defined as Dirac delta of t minus a equal to 0 when t not equal to a, and area under this function is 1, and if it is actually f of t, this function will have value f of a. The area under the function is 1. At t equal to a itself, we do not define Dirac delta function. The Dirac delta function is defined through an integral. This Dirac delta function can be used to model impulsive loads on the structure. Okay. So, how do we get the so called response of the system to an impulse? So, I will model f of t as a box function, and the response will be accordingly f into g of t for t less than or equal to tc, and this is this for t greater than tc. Now, I will rewrite f of t as f tc divided by tc. Now, the limit that I am talking about is tc going to 0, f tc going to 1, and the forcing function goes to du by dt, which is Dirac delta function. Under the same limiting condition, what happens to x of t? It will be f of tc into g of t minus g of t minus tc by tc. So, under this limiting condition, you see that this quantity is nothing but dg by dt. This h of t is therefore derivative of initial response. This we call it as unit impulse response function, and the expression for that is displayed here. This is g of t and this is the differential of g of t. And for an undamped system, when eta is 0, omega d will be omega, this is 1 by m omega sin omega t, and that is this sinusoidal function that is shown here. For a damped system, it is a exponentially decaying harmonic sinusoidal function. So, in the next class we will see how the impulse response function can be used to construct the response of the structure to an arbitrary load f of t. So, the lecture ends with this.